Heidi Roop. I'm an assistant professor at the University of Minnesota. I'm based in the Twin Cities, but I also serve as the state of Minnesota's extension specialist for climate change and adaptation. I lead an organization called the Minnesota Climate Adaptation Partnership, and we are working to expand dedicated climate services and the delivery of future climate change information for use by folks like yourself. And so adding to the amazing mix of resources and people and experts that are active in this space, as you saw from the introductions in the chat, we are have a wealth of information available to us to guide our journey towards achieving climate resilience for our communities and our landscapes. I have the challenge of trying to cover the sort of big 30,000 foot view, quite literally, of climate change and sort of why we're here, the state of knowledge around what we understand about the kind of global scale and impacts of a changing climate. And then we're going to zoom down into what does that mean for us here in this geography for managing our resources, our communities, our built environment, our natural world, and thinking about how to prepare for and navigate through successfully what will be a very different climate future for our region. So as I said, I lead an organization called the Minnesota Climate Adaptation Partnership. You can learn more about our work at climate.umn.edu. Some of the information that I'm sharing with you today, especially my second presentation, is available there, including climate projection information for the state of Minnesota. And stay tuned because we do have funding from the state to be developing really high resolution future climate projection information using the most recent global climate models. And we should have information available in the sort of coming year. Our supercomputer is busy at work right now, helping to generate those data. So we also provide best practices and other resources to help you on your journey towards understanding impacts of climate change, as well as adaptation opportunities and priorities. So we're going to just do the big picture climate change. What's the state of the knowledge? Why are we here today? What are we looking forward to in the future? I've pulled this first bit primarily from a recent report by the Intergovernmental Panel on Climate Change, and Julie mentioned this, often known as the IPCC. So you'll hear me say that, and probably the other presenters in this session. And they published a synthesis report. This is a series of reports that come out over a regular interval. There are many more coming out in the coming months as part of this sort of synthesis of our state of knowledge. And this was a publication specifically synthesizing our state of knowledge around the physical science basis for climate change. And when you take this sort of several thousand page report and appendices and data pieces, this is my sort of Cliff Notes version of what I think we need to know, which is that it's very clear that the observed changes that we're observing change in our natural system and in our climate system, and we know that that change, what's driving that change is us. We understand that climate change is here. We understand that there are fingerprints and impacts of a changing climate everywhere in the globe. We understand that we have committed to change. So we have locked in a certain amount of change, and I'll show you a little bit about that in the subsequent slides. We also know, because we know the source of the problem, we know what we can do where there are opportunities to prevent the problem from getting worse. So we know very clearly that if we emit more greenhouse gases, the warmer it will get and the worse the impacts. We also still have this opportunity of time, and the next decade is really important for trying to reduce our emissions of greenhouse gases, those heat trapping gases that are warming the atmosphere, that lead to global warming, that then stems into these impacts that we then have to plan for and manage for moving forward. We know that there's a need for doing this work, reducing emissions urgently. And I would also argue that we know we urgently need to be thinking about how we prepare for the changes that we've set in motion. And that is really what you're going to learn about people who are doing that work today, sharing some of those stories, those opportunities, and also thinking about what are our barriers and how do we move forward together collectively. So we know it's us. This is the strongest statement the IPCC has made related to the human-caused nature of the climate changes that we are observing today. And they have stated that it is unequivocal that human influence has warmed the atmosphere, the ocean, and land masses. We also, and this is my pet science, this is where my scientific background comes from, which is past climate change. We also know that the rate of warming that we're observing today is unprecedented in at least the last 2,000 years. So we know it's us, and we know it's happening quickly, and we know we're sort of out of the realms of the sort of recent geologic past. And we also know there are clear connections between the human-caused climate change and the changing patterns and extremes, some of which we've already discussed today, and some of which we see in the news on a regular basis. Last summer, of course, was no exception. We're seeing extremes in heat waves, heavy precipitation, droughts, and tropical cyclones. So we're seeing these clear connections. We also know that human-induced climate change is affecting many weather and climate extremes in, quote, every region across the globe. So it's here and it's everywhere. And so this management challenge, this reducing the problem challenge, is everyone's challenge, right? There are no winners when it comes to a climate changed world. We have already warmed the globe by around 2 degrees Fahrenheit. This is the whole global average. And this has all occurred since the late 1800s. And we know that the 2011 to 2020 decade was more likely than not the warmest in roughly 125,000 years, spanning back to the Eemian time period. I'm working on collecting an ice core to help, in fact, verify that. But it is warm, it's very warm. We know we've committed to change, so we know we're on a path towards further warming. So the global average temperature will continue to increase until at least mid-century, which is around 2050, under all emission scenarios. So even if we turn the dial today down and we have 0 carbon emissions or greenhouse gas emissions, we've locked in some warming. However, we know that the more we emit, the warmer it will get. And this is the opportunity that we have as a global society today. We still get to choose the outcome of a warmer world. We also know that we have to do that urgently. So global warming policy targets will be exceeded in the 21st century unless deep reductions in greenhouse gas emissions occur in the coming decades. So the time is now. And ultimately, and the sort of framing the discussion for today, how we feel and how we navigate climate change really depends on 2 parts of an equation. How well we prevent further warming, this is mitigation, this is a reduction of greenhouse gas emissions, and then how well we prepare for the changes we've set in motion. It's not an either or, it's not a one or the other. We have to be working and investing and bringing our expertise to work towards both of these pieces, the prevention and the preparation, in tandem. And if we do that, we will be likely to have climate ready communities, infrastructure, and ecosystems. And with that, I'm going to pass it to Kim to start telling us about how this big picture fits into our local story.
All right, thank you so much, Heidi. Well, good morning, everyone. I'm Kim Channel. I'm a climatologist with the Great Lakes Integrated Sciences and Assessments, or GLESA team. We are a NOAA-funded program out of the University of Michigan and Michigan State University with a mission to help build the region's capacity to prepare for and adapt to climate variability and change. So Heidi just walked us through a really good global scale overview of climate change and gave us a really good base of knowledge to build on. And now I'm going to scale us down a bit to what that means for climate trends at the Great Lakes regional level. And at GLESA, we like to structure these conversations around 3 particular questions. What has happened? Historically, how has the climate already changed? What could happen? What do climate models project for the future? And what are the impacts that we actually experience? So this presentation is not by any means a comprehensive answer to all of those questions, but hopefully it can lay the groundwork for understanding some of the more prominent trends for the Great Lakes region. And we're just going to start with our basics for regional temperature trends. So average temperatures in the Great Lakes region have increased by an average of 2.3 degrees since 1951 and are projected to further increase by 3 to 6 degrees by the mid-21st century, or about 2050. But the whole story is not quite that simple. This doesn't just mean that in 2050, February 9th will be 26 degrees instead of 20. This really is just the average annual change. So there are both spatial and temporal variations that need to be accounted for when we're looking at these trends and what they mean for us. And one of those variations is seasonal. So while the annual average temperature has increased by about 2.3 degrees, the winter average has increased by 3.9 degrees in the region. And this generally tells us that our winters are warming faster than the rest of the seasons. And in addition to that, winter warming is also stronger in the northern parts of the region compared to the southern Great Lakes. And there's also a similar case for lake temperatures as well, with Lake Superior seeing warmer surface water temperatures in recent decades following these increases in air temperature. And now let's look at changing precipitation patterns. So annual precipitation has increased by about 17% since 1951. But again, this is just Great Lakes wide average. There is some spatial variability among the different parts of the region. And you can see that in this map here of annual average changes in precipitation observed since 1951. So these darker greenish blue areas saw greater increases over that time period than the lighter areas. And again, this is annual average over many decades. So this doesn't really tell you anything about extremes or seasonal shifts that might have been occurring during this time, but you can see that they are all positive changes. So that means increases in precipitation have occurred across the entire region. And this trend is expected to continue into the future. So this is a map showing projected annual total precipitation changes for the region by that 2050 timeframe. So similar to the last map, these darker blue areas mean greater increases. Lighter blue is still increases, but less so. And it's not quite the same everywhere. But again, this is just overall annual precipitation. Where we see some of the greatest impacts arise is from rainfall occurring in extreme precipitation events. So the volume of rain falling in the heaviest 1% of precipitation events has increased by an average of 24% since 1951 across the region. And the frequency of these events has also increased over that same time period. But to really understand increases in extremes, particularly in, extreme rainfall, you really have to zoom into that local scale. So that's what this map intends to do. It's showing those local scale changes from individual station observations. So these dots show the percent change in the intensity of the heaviest 1% of precipitation days for that for the 1991 to 2020 period compared to the 1951 to 1980 period. So red dots here represent increases between those two time periods. Blue dots represent decreases. You can see there's quite a bit more red dots here than blue, and the larger the dots are, the greater the change. So these large red dots that you see throughout the map correspond to pretty major increases in extreme precipitation intensity over the last several decades. And then just to close the loop here on precipitation, warmer conditions are affecting the type of precipitation that we're seeing fall in the winter months. So these two images show the shift in average annual snowfall from the 1961 to 1990 period on the left to the 1981 to 2010 period on the right. So you can see kind of the progression from left to right and the changes that have occurred between those time periods. So in the lake effect zones, especially along the north and west coast of Michigan, or even a bit in northern Wisconsin, you can see that there's actually been an increase in snowfall. And this can at least be partially attributed to warmer lake temperatures and less ice cover on the lakes, allowing more moisture to be available for cold air masses to pick up as they move across the lake and producing more lake effect snow. But if you look farther south or even farther west in the region outside these lake effect zones, you can really see the bands of snow just shifting northward. So each area is getting less and less snowfall. This is generally because more winter precipitation is starting to fall as rain instead of snow as winter temperatures rise. And that's a trend that we expect to dominate in future decades, even in those lake effect zones, just because the amount of winter warming outweighs the lake dynamics with increased lake effect snowfall. So the Great Lakes themselves do have a role in regulating our climate and affecting the changes that we see in the region. And snowfall is a pretty great example of that. So that was just a very quick run through of a few of the major region-wide climate trends, but now we'll get into a few impacts that these trends cause in the Great Lakes region. And I want to note that Most of the impacts mentioned here are not caused by climate change, but they are exacerbated by it. And a good example of that is algal blooms to start us off. So harmful algal blooms in particular can negatively impact human health, ecosystem health, as well as local economies in many coastal regions, including the Great Lakes. And algal blooms form when nutrients like phosphorus run off into a lake from surrounding land, primarily agricultural lands. And then those nutrients sit in warm, shallow surface water where algae can feed off of and grow. And algal blooms have been occurring for many years, but the factors that lead to their formation are enhanced by some of the regional changes that we have observed in temperature and precipitation. So on one hand, you have more rainfall and specifically earlier shifts in spring rains and extreme events, which increases runoff from the surrounding basin and therefore increases nutrient loading in the lakes. And then on the other hand, you have lake temperatures that are also warming, sometimes even faster than the surrounding air temperatures are warming. And these warmer water temperatures cause there to be less overturning in the lake, so more stratification of the layers, different layers of the lake. So that leaves those nutrients to just stagnate in warm, shallow surface waters for algae to feed off of and grow out of control. So this is normally a problem for warm, shallow waters like Lake Erie and the Gulf Coast, rather than the northern Great Lakes that are deeper, colder, and lower in nutrients. But even Lake Superior has experienced a number of algal blooms in recent years, mainly from heavy precipitation events, which increases runoff and the nutrient loading in the lake. And then lastly, large algal blooms also use up a lot of dissolved oxygen in the water, leaving little oxygen left for fish and creating some hypoxic dead zones where fish cannot survive. And then beyond just fish, changes in temperature and precipitation patterns also have widespread impacts on forests and wildlife. So as we see warmer temperatures, forest and wildlife will begin to migrate northward. So certain species of trees, mammals, birds, and fish that have been in some areas for centuries will start to be displaced by species that are more suitable for the new state of the climate. And this puts a lot of stress on biodiversity, and some species just won't be able to adapt or move fast enough to keep up with the pace of change to their environments. And then a topic that has gotten a lot of attention in recent years is Great Lakes water levels. So lake levels in the Great Lakes fluctuate based on the competing dynamics of how much water is entering the lake versus leaving the lake. So most simply put, the biggest drivers are water entering the lake system from precipitation and runoff, and then leaving the lake system when it evaporates from the lake's surface. So each of these three components is in turn affected by regional climate changes. So any future changes in lake levels will depend on how one or more of these processes will dominate another. So unlike the oceans where sea level is expected to rise as global temperatures warm, the Great Lakes will not just rise or fall. They will continue to fluctuate. There will still be periods of highs and lows in the future. The question really becomes, how will the changes to the components of the water balance affect those fluctuations? And most likely that is with greater variability and extremes than in the past. So higher highs, lower lows. And water levels on our Great Lakes can have a pretty vast range of economic and environmental impacts. Low lake levels can create issues in boating, tourism, and shipping. Marinas and canals have to be dredged more often. Freighters have to reduce their cargo loads and ultimately their profits to navigate shallow waterways safely. On the other hand, high lake levels can lead to shoreline flooding and erosion, especially when it's coupled with high wind or wave events. And then lake levels also affect ecosystems, coastal wetlands, and fisheries in the lake, especially with providing protection for breeding zones and habitats. And then ice cover is also important to regional activities and economies, with ice cover protecting certain fish species and wetlands, providing a platform for ice fishing and other winter recreation, and of course, presenting an obstacle or even just an outright barrier to shipping and navigation during the winter months. And average Great Lakes ice cover has declined since the 1970s when modern records began, but it's not a linear trend. So even though ice cover has decreased on average, it will not necessarily always be low. There are some years like 2014 and 2019 when we were visited by cold polar air outbreaks from the Arctic that caused almost full ice coverage across the lakes. So even though we're seeing less ice cover on average than in previous decades, there will still be some individual years of high ice cover due to natural variability and cold air outbreak events. And I want to expand a bit on that topic of shoreline flooding and erosion because that is influenced by both lake levels and ice cover. So high wind and wave events during high water conditions accelerates erosion to both public shorelines or private residential properties. And this can be particularly prominent in the winter, especially when there's not solid ice cover on a lake and it's kind of just broken up in pieces. So if there's a high wind and wave event during winter with ice conditions like that, ice can just get pushed up onto the shore and chip away at land, infrastructure, piers, breakwaters, that kind of stuff. And many of you are likely very familiar with the high lake level conditions and several bad storms on Lake Superior over the last few years that contributed to local flooding, lots of shoreline erosion, and damage to some popular tourist spots. So that's shoreline flooding, which is primarily driven by high lake level conditions or winds and storms. But we also have to consider inland flooding and extreme precipitation impacts. So the increases in extreme precipitation we are seeing can lead to short-term flooding. It can damage roads, bridges, other infrastructure. It can interfere with transportation and emergency services. And some municipalities have combined stormwater sewage systems. So an overflow from a heavy rain event could lead to the release of untreated sewage. It could cause water quality and public health issues. And lastly, cities have to rely pretty heavily on stormwater drainage systems because of all the impervious surface, all the concrete. Otherwise, that water would have nowhere to go. But even these drainage systems can be overwhelmed. A lot of older stormwater systems were designed based on historical conditions and not on our new present and future conditions. So they don't necessarily have the capacity to handle these larger volumes of rainfall within a short period of time that we're seeing more often. So as Jason mentioned at the top of this forum, a lot of communities are now pursuing adaptation efforts that take climate change into account in things like stormwater drainage planning or flood management. And that's really what this comes down to and how we move forward as a region to prepare. Because climate change just brings a lot more uncertainty and new issues to the table than we're used to dealing with in the past. And it's important to be informed and prepared for these changes in order to mitigate the impacts that they have on us. So I just want to say thank you for your time. For more information on all the topics covered in this presentation or many more topics that I did not even get a chance to touch on, you can visit our website here. And if you have any questions, you can reach out to our general GLESA email here, or you can reach out to me directly. I've also listed my email. So thank you so much. I'm going to pass it back over to Heidi.
Great, I'm back. You can't get rid of me that easy. So Kim just gave us a great sort of Midwest overview, and I've been tasked with sort of bringing in some Minnesota specifics, similarly the observed changes as well as projected change. I have 6 minutes. I'm going to start a timer for myself. And so please, if you have questions or you'd like slides or additional slides, happy to share those with you. And Julie, just a note, I'm happy to record the longer presentation if that would be useful to folks at another time. So I'm going to do the quick drive through. So we're going to focus on the geography of the state of Minnesota here for this particular presentation. We're going to get a deep dive into some of the Wisconsin perspective and impacts in the next presentation. So Minnesota, similar to what Kim outlined, we're seeing the same trend and pattern, right? We're part of the same geography. When we zoom in to the observational record for the state, we can see that our average annual temperature, if we look at the whole state, has increased by nearly 3 degrees Fahrenheit since 1895. We have an incredibly robust, rich record of observational. So we've got lots of people recording temperature, precipitation, snowpack, you name it, across the state. So we have this really robust record of observations. And we can unpack the state into these sort of south to north trajectory and see that, as Kim noted, not only is it interesting to look at the average annual temperature, but starting to unpack some of the seasonal variability as well as the extremes, sort of those low lows. And I think the big part of the story that you'll hear, the slide is from modified from the Department of Natural Resources, from Kenny Blumenfeld, who's one of our state climatologists. We really like to talk about the sort of loss of winter and the absence of those low lows, those iconically cold Minnesota winter days. They're just not happening as often. And so when we look at winter low temperatures in the northern parts of the state, those winter lows are 7.3 degrees Fahrenheit warmer than they were in the late 1800s. And so we're seeing this pattern of warming emerge, and just looking at the average annual information isn't necessarily so helpful. We're starting to see those summer highs change, and this is something I'll show you in a slide in a minute. We're expecting to experience more of these extreme hot days in the summer, and so we expect these maps to continue to get redder and redder as we move forward into the future. The state as a whole, this is using similar modeling techniques to some of what Kim showed, shows that if we look towards the mid-century, around the 2050s, the state on average, we look at our average annual warming, will be between around 4 to 6 degrees warmer, depending on the emissions of greenhouse gases, with more emissions corresponding to an overall larger increase in the average annual temperature by the mid-century. We expect to see, and this is the kind of thing that makes my heart stop a little bit, the average number of days per year when the daily high exceeds 100 degrees Fahrenheit. This is obviously important for human health as well as ecosystem health and animal health and well-being. We can see that by the end of the century, under high emissions, we are going to be experiencing in many parts of the state sort of around 18 more days of highs in excess of 100 degrees Fahrenheit. I'm pretty sure that's not why people live in or move to Minnesota. So again, we still get to choose how hot that map gets moving forward based on emissions. We know that Minnesota is getting both warmer and wetter, and our 10 combined wettest and warmest years, we look at those two together. Those 10 combined warmest and wetter years have all, on record, have all occurred after 1997. So we're seeing this pattern of emergence. We can also look at these observational records and we see that there's more winter rain and less snow on the ground. This is true in Duluth, and I can provide those who are interested with some data to show that. We also expect, as we move forward into this warmer world, we're looking at projections of snow cover. This is basically looking at a change in the number of days with snow exceeding 1 inch. So this is snow, we need snowpack on the ground greater than 1 inch. As we march forward into the future, we're seeing by the end of the century, under high greenhouse gas emissions, that there are probably going to be around 60 days per winter with basically no snow cover. Those are the kind of green, light green colors you see on the map. And so as we march forward, as Kim already outlined, there's all these impacts that stem from the sort of changing patterns of precipitation, changing in seasonal variability, changes in the season length that really translate into impacts and things that we need to proactively manage for. We know that we are both observing and anticipate in the future more increases in those very heavy precipitation events. So this is, of course, a big challenge for things like stormwater, wastewater management. And these are projections showing average annual, the largest 5-day rainfall total out into the future in comparison to 1990. And so again, as you see marching towards the future, the map on the far right, that's mostly green with lots of blue, and the geography we're discussing today, we can see under high emissions near the end of the century, that largest 5-day rainfall total could be around 55 to 75% greater than it was in the 1990s. So right, this has real implications for how we design and build and manage our landscapes today. And of course, what we are already living through, as Jason pointed out, and what we are planning for in the future brings real costs. We know very clearly that it is cheaper to be proactive than it is to be reactive. And so we know we're expecting more precipitation in the future, up to 30% by the end of the century in winter and spring precipitation. That's across the Midwest as a whole. And we expect average annual damages from increased flood risk alone to exceed $500 million by 2050. And that's every year in this region. And interestingly, the Midwest is among the regions with the largest expected damages to infrastructure including the highest estimated damages to roads. And this is from the National Climate Assessment and the Economic Assessment conducted by the EPA for the fourth National Climate Assessment. And these numbers will be updated in the forthcoming assessment that will be released in 2023. We also know in the Midwest, we have these wet extremes, right? This is something that is the hardest thing to manage for, is this oscillation between the extremes. So the dry extremes and the wet extremes. We know wet extremes have increased in magnitude over the past 70 years, while dry extremes have remained largely the same. I know this is hard after having just lived through a pretty severe drought, and we're kind of scratching our heads wondering what's going to happen now with drought over this winter. But this is also true for Minnesota. We're seeing those wet extremes. The signal is yet to emerge in our dry extremes, but we also know that we're oscillating in the region more quickly from the wet and the dry. And so what does that mean? The sort of quick summary is that Minnesota, we're already warmer and wetter. We're already experiencing more precipitation extremes. We expect to have to manage for those in the future. We're expecting further warming, hotter summers, and less snow cover. And we know that we need to manage for variability, the same way that we talk about, that Kim mentioned with lake levels. As we think about droughts and wet extremes, variability is going to be the name of the game. And we need to be able to anticipate how we hold the two truths in our hand at the same time, right? It could be drier, possibly for longer, but we might swing back into these wet extremes more quickly. And so we have to be ready for basically the worst case scenario, which is the wet and the dry. And of course, there are more data, tools, decision support resources coming online soon by my group, by other groups, to really help us unpack this really complicated future. Planning for this is really difficult, and that's why we're having these important conversations today. And I will just end with saying it has never been more critical for conversations like this to happen, for us to combine perspectives, resources, ideas, creativity, to craft inclusive responses to the emerging risk of climate change. We know it's here, we know it's us, we know we can prevent it from getting worse, but we also know we need to manage for change in the near term and the long term. And so with that, I'm going to pass it to Megan for some discussion of impacts and also focus on Wisconsin, which is where I'm from. So I'm interested in that. Sorry, Minnesota. Thanks, Megan.
Thank you, Heidi. That was fantastic. So I am Megan Salmon-Tumis, and I am an assistant professor of climate science at Northland College. That's in Ashland, Wisconsin, on the Chequamegon Bay of the South Shore of Lake Superior. Today, I'll share with you some of the ways that climate change is affecting our region. It'll be a little bit focused on northern Wisconsin and what we can expect in the future. So first, a bit about, there we go, about how climate is changing in Wisconsin. As was highlighted by Kim, temperatures are rising and winters are warming the fastest. Precipitation in general is rising slightly. Northern Wisconsin saw a 5% increase in annual precipitation since 1950 and can expect another 5% increase by mid-century. The changes are not evenly distributed among the seasons. In fact, in Wisconsin, summers have gotten drier. But with winter, the trend is clear. In the most likely scenario, winter precipitation in northern Wisconsin by mid-century will be about 10% greater than it was at the start of this century. For better or worse, the increase in winter precipitation does not necessarily mean more snow because winters are warming. So this means that more of the winter precipitation will fall as wintry mix and rain. If you think back to mid-December of 2021, the Duluth area had thunderstorms bringing record warmth and heavy rainfall, and there was 2 inches of rain in the Iron Range. That was December 15th to 17th. So we are seeing also increases in these heavy rains has been highlighted in frequency and intensity, and I'll talk more about that in a bit as well. So these are the basics, but what does all of this mean for you and your community? Yeah, here we go. Wait. Okay. Okay, sorry about that. So the consequences and outcomes of these changes in climate are called climate change impacts. The impacts are too numerous to list in one session. They affect Earth systems, ecosystems, societies, economies, and built environments. Here, I'm going to focus on just those impacts that are the most certain and the most concerning for our communities. You're going to recognize a lot of them from these talks and from challenges that you're seeing in your own community. My goal here is to show you how they're all connected to this global process of climate change that you've been hearing about, because seeing these connections is going to help you to develop plans for resilience and access targeted resources. First, we'll look at flooding. As Jason shared earlier, our region has seen several disruptive and even deadly floods in recent years, 2012, 2016, and 2018, affecting the southwest shore of the lake. These flood events can lead to damages to transportation infrastructure, such as roadways and bridges, as well as travel disruptions, loss of life, threats to safety, and decreased water quality. So they can affect key tourism amenities, such as washing out of popular trails or flooding of campgrounds, and they can affect wastewater treatment facilities through overflows or damages. They also change floodplain boundaries, and water intrusion in buildings can lead to mold, affecting indoor air quality. Floods are triggered by heavy rain events, and in Wisconsin, in northern Wisconsin here along the south shore of the lake, these rains of 2 inches or more were occurring at the start of the decade around 8 to 10, start of the century, sorry, around 8 to 10 times per decade. And by mid-century, their frequency will rise more to 12 to 14 times per decade. So rains of 2 inches or more can lead to severe flooding when they occur on back-to-back consecutive days, like we saw in 2018. More concerningly, the even more extreme heavy rain events of 5 inches or more, like we occurred in 2012 and 2016, will double in frequency by the middle of the century. This intensification of the rain events is tied to the rising temperatures because warmer air can hold more water vapor, and especially with our rapidly warming lake nearby, this capacity to hold more water means that there is going to be more water in the atmosphere ready to fall as rain when rain events occur. But climate is not the only factor that affects flooding. Once that rain hits the ground, what happens next is influenced by factors literally on the ground. So the type of soil in your area affects how quickly the rain can soak into the ground, with clay soils being the most prone to flooding. Next, it matters what the ground is covered by. Healthy vegetation is the best at preventing flooding, especially forests and wetlands. So having healthy forest and wetlands areas can help communities to be more resilient to heavy rains. But in some areas, land needs to be hardscape. Then including green infrastructure, such as rain gardens, can help to slow the flow from the area and reduce the chance of damaging floods. Once the water is flowing over the land surface, the impact it has will be affected by the infrastructure it encounters. If it encounters culverts that are not large enough to allow the heavy flow to pass through, it could lead to washouts. We may not have very much control over our climate or our soils right now, but we can work toward increasing the proportion of our lands covered by healthy forests and wetlands. We can include green infrastructure in our city planning, and we can scale culverts appropriately for the climate we face. There are many resources available to help communities prepare for these heavy rains by improving their stormwater management, maintaining evacuation routes, limiting power outages, and reducing property damage. Many of these are listed in an adaptation planning guide that I'll share at the end of the presentation. Here are 2 that I want to be sure you know about. The Northwest Regional Planning Commission hosts a site where communities in Northwest Wisconsin can view flood risk maps that help to identify infrastructure and buildings at risk. Use this link that should be getting dropped in the chat box here. Thank you. In order to access map viewers for 2 levels of severity of flood events. And another great Wisconsin resource is the Community of Practice coordinated by the Wisconsin Coastal Management Program. This group runs workshops and provides resources that help in identifying at-risk culverts and justifying their replacement. Again, the link there is in the chat box. Next, we'll look at water quality. Climate change, as we've been hearing, is bringing algal blooms and more waterborne diseases to Lake Superior. And so we know how we can see the algal blooms because they look like pea soup or spilled paint in the water, but other microbes can also be present in the water without being visible, which is why waters are tested regularly for E. coli. E. coli bacteria are not the only microbe of concern, but their levels in the water tend to indicate the presence of other harmful microbes. Clean water is essential, and it's a resource that the communities around Lake Superior especially expect and rely upon for their enjoyment, their tourism, and for life. Algae blooms can affect lake access for water-based activities, and if they were to produce toxins, that would threaten drinking water and fisheries. While the algae blooms that have been found in the open waters of Lake Superior so far have not been detected to produce toxins, we did just discover the first toxic bloom last fall in an inlet of Western Lake Superior. And Lake Superior waters are not the only waters susceptible to the increase of water quality concerns. Groundwater wells also are more prone to contamination under a warming climate. We have just looked at how heavy rains are on the rise, and when mixed with certain factors on the ground, this can lead to flooding. The runoff produced by heavy rains brings new nutrients into the lake, even if it doesn't come from a heavy agricultural area. These nutrients can feed the cyanobacteria. Of course, if flooding produces sewage overflows, this also directly harms water quality. And as Kim explained, another important climate factor is warming waters, and Lake Superior is one of the fastest warming lakes on Earth. And those warmer waters provide a more hospitable environment for the microbes, not just the cyanobacteria that produce the algal blooms, but also other various bacteria and viruses that bring waterborne diseases. We've already talked about how communities can reduce runoff during heavy rain events, and those factors apply also to reducing the effects on water quality. Other things that communities can do is to improve their stormwater management systems to prevent the sewage overflows during heavy rains. Other sources of microbes can include wildlife and pets. So communities may need to close beaches due to exceeding E. coli limits due to contamination sources such as waste from Canada geese, from seagulls, or from pet dogs. A helpful resource for communities looking to better protect freshwater quality is the Source Water Collaborative. Their website is a learning and exchange network that can connect you with data and guides and other resources. It's also important to know that area academic institutions can be powerful partners in these concerns. So the University of Minnesota Duluth's Large Lakes Observatory, as well as Northland College's Burke Center for Freshwater Innovation, both partner with local communities on researching the sources of algae blooms and E. coli outbreaks in the lake. Knowing the source of the problem is an important step in addressing it. So if your community is having to close beaches often and you don't know what your source is, I encourage you to pursue a partnership like these to find out more. Next, we'll dive into lake levels. Lake Superior water levels hit a record low in 2007 and then rose to a record high in 2020. And now the levels are dropping quickly. This January, water levels are 28 centimeters lower than they were a year ago. That's nearly a foot drop in 1 year. The lake levels have always fluctuated, and yet these record levels and fast changes feel unprecedented. And if your community has shoreline, then you probably know what these lake level changes can bring. Fast rises in levels lead to shoreline erosion and damaged infrastructure. And when they remain high, waterfront is reduced and beach erosion is worsened. Kim shared earlier about the complex climate factors that affect lake levels, such as increases in precipitation and increases in evaporation. Lake levels respond to this tug of war, and as climate change is tugging harder on both ends of the rope, lake levels are fluctuating more quickly and reaching more extreme levels. Of course, how these changes affect your community depend on the physical characteristics of your shoreline, its rock or soil type, its direction with respect to the winds, its vegetation, etc. It also depends on the design of your waterfront infrastructure. So you can check your community's marinas, boat launches, and shore protection to ensure that they are built to withstand these changes. One tool that could help you plan for these changes is NOAA's Digital Coasts Lake Level Viewer. With this tool, you can set the lake level to see what you can expect the water depths to be near your shoreline. Make sure to look at both high and low lake levels to see how your community could be affected. And there again is the link in the chat box. Thank you. Other effects of climate change come from warming winters, in particular snow and ice becoming less reliable. You won't be able to sell off your city's snowplow fleet anytime soon, but you could start to see the effects of these changes in the coming decades. Dry spells, warm weather, and rain on snow are winter weather events that hurt ski areas. On top of that, the warming trend is leading to shorter ski seasons, shrinking at both ends in a lot of places. Of course, it's not only the ski resorts that are affected by this. Area businesses also rely on good snowmobiling conditions for their winter business activity. And there's lake ice, records kept since the mid-1800s detailing Lake Superior's ice duration show that it has decreased by 2 months. This affects travel on the lake, such as ice roads, and it affects the ice safety for activities like ice fishing. To address these concerns, a place to start is by assessing your vulnerability to them. On the left here, you see a map of places that have historically had conditions that support winter tourism activities in green shading with stars that show current ski resort locations. On the right, you see how the green areas will recede by mid-century, with fewer locations having the consistent winter conditions needed for viable businesses. Other steps you can consider taking are planning for future conditions. This applies to all of these areas. Encourage area businesses that rely on snow and ice to diversify so that they can remain viable. If your community hosts winter events, consider promoting alternative events in the case of unsupportive winter weather. And finally, engage in creative approaches like building community vitality and placemaking. Climate change is also affecting our area's ecosystems. Northern species, especially boreal species, are the most threatened, and their ranges are shifting northward out of our region. Forests are being subjected to more damage by pests, diseases, and invasive species, and these are being fueled more by climate changes. And some species that are of key importance to area cultures are at risk as well. An important example is monoman or wild rice, which is highly sensitive to sudden changes in water levels and does not thrive following mild winters. Other examples of important species that are sensitive to a warming climate include brook trout and blueberries, among others. Partnering with natural resource specialists and implementing traditional ecological knowledge could be helpful approaches to addressing these concerns. As I said earlier, there are far too many climate change impacts to discuss in one session. Some other changes that are being fueled by climate change the area communities should prepare for or have in their mind include an increased demand for energy in the summer as temperatures rise, changes in population as climate change impacts in other regions for people to move to the Great Lakes area, increased tourism to high latitude destinations that are better protected from heat, air quality concerns from increased wildfires and pollen, both fueled by climate change, increased mental health concerns such as anxiety, depression, and PTSD that are all affected by climate change, and an increased need to protect vulnerable populations during instances of extreme heat. So there are resources to help with these concerns. A great one is the website and reports from the Wisconsin Initiative on Climate Change Impacts, or WICI. They are going to be updating their most recent overview 2011 report, and that'll be released in early February. So check on this website frequently in the coming weeks, and there's going to be some great resources posted there. And there already are. The 2011 report is also very helpful. And then for information that's really specific to our region, you could look at this adaptation planning guide that I produced with my colleague Robin Kemkes. It's for the Chequamegon Bay area of Lake Superior. And I hope you'll feel free also to reach out to me directly with any questions you have. Thank you.